All right. So guys, today we're going to be doing our electrostatic force interactive. So we had, like I said last week, we had talked about friction, conduction, induction. We talked about the anatomy of an atom. All right, the electrons have our negative charge, our protons have our positive charge. Now, what we're going to see now is how these charges kind of interact with one another. Not just as far as the charging point is concerned, but the force that they exert on one another. So that is what the purpose of this is, to try and determine the relationship between the force of attraction or repulsion between two charges and the factors that affect this force. Okay, so we have the link that was embedded. It's on PhET. Go to the macro scale, and hey, this is what we got. Now, what can you tell me right now just about the force? Is this an attractive force or repulsive force? Just by looking at the picture.
It looks like they're going together.
They look like they're going together, so what would we say? Attractive. And you're right. Now, what do we notice then about the numerical pieces down at the bottom? One is, and one is, and what did we say last week? That opposites attract. Very good. Okay, so if opposites attract, like charges should do what again? Not subtract, but repel. Yes. Okay, so if one of them is negative, what if I make both of them negative? Now look at the arrow. Now it's repulsive. Okay, so it's repulsive if they're both negative. What if they're both positive, though? It is also repulsive. So if they have the same or like charge, both negative or both positive, it is a repulsive force. And if one of them is positive and one of them is negative, that's opposite, and they will be attractive. Okay, and then also it says you can like click around and move around the whole the move. You know, we can do the move here. Move the distance closer and farther apart. And what do you? Well, let's just see. What do you notice right now? What happens to the force as they get close?
It repels even greater.
Right? Yeah, the force goes up big time. As we get farther away, does the force change by that much?
No.
All right, so let's put this John at 0. Let's put this dude here at 10. Right? Yeah, they're the same value. What if I move the one that's at 10 to 9?
Still the same.
Still the same value. And did it get bigger? The force? It was at 53, and now it's at...
Oh, yeah, it got bigger.
Okay, so now what if I make it closer? So what is, all right, 53 to 66 is how much? About 13? Okay. So now let's go from 9 to 8. 66 to 84, how much is that?
18.
18, okay. Now let's go from 8 to 7. So 84 to 110. Increase even more, right? Okay, so now let's go to 7 to 6. Almost 50, or almost, no. This is 150, 110, about 40. Okay. What about 6 to 5?
What do you go, 150?
About 150 to 215.
65.
Okay, from 5 to 4.
215, so 100.
215 to 330. Dang, wow. Why did that one jump so high? Okay, well, let's see. From 4 to 3. Is that 330? Damn. What about from 3 to 2? Damn. And we can't even quite get to the 1, but from 2, right, we're at this. Dang. So what can you tell me that as the two charges get closer together, what happens to the force? It increases. Does it increase at like roughly the same? No. When did it really start increasing? When we started getting right, 5, right, over here it's like, oh, it increased by a couple, it increased by a little bit more, and then all of a sudden it's like, yo, whoa, dang, yee, or sheesh. Okay, so you understand and see the idea that distance plays a dramatic change or has a great effect on the force between them. Okay, well, what can we tell me right here? Now let's say we just set this dude to 1. And let's say we're going to set this dude to 1. What is the force between them? 22, yeah? Okay. Now, what if I double one of the charges? What did it change to? 44. Okay, what if I tripled one of them?
67.
Okay, well, what was the original value again?
22.
22.469. So get that out I'm going to have this in my calculator, right? So I'm going to do 22.469. I'm going to multiply that by 2. And my calculator says 44.938. Okay, bet. Now I'm going to multiply it by 3 in my calculator. My calculator says 67.407.
Divided by 3.
Multiplied.
Times 2.
Okay, so what if I multiply that by 4? I should get roughly 89.876. Huh. But wait a minute. When I doubled or decreased the distance by 1 or increased the distance by 1, it was the increments weren't the same. They're the exact same, right?
Maybe
So
because they're not opposites.
maybe because they're not opposites. Okay, well let's.
They're not attractive. Right?
Maybe we could look, right? So right now we have 1 and -1, right?
Now they're attractive.
Guess what? It's the same, but it was the same number,
Sure.
right? And what was the last number we did? 22.469 times 4. So if we crank this to 4, we should get our 89.876. Oh, dang. So these guys seem to increase by the same amount each time as I change just one of them. Okay, so let's go back to this. What if I doubled one, the force doubled. If I double both of them, what should it be, do you think? So I doubled the first, charge 2, yeah? And it's 44.938. And when I quadruple this one, I increase this by 4 times, I get this number, the 89.876. What if I doubled both of them? What do you think would happen? Would it increase by just doubled? Or would it be more? I'm thinking more. All right, so let's double this one. You saw that this doubled. But now let's double the second one.
So 44 was the one that doubled.
44 was the one that doubled. So go back to this one, go to the normal. If I only increase one of them by a factor of 4, I get this 89.867. If I double this one and this one, I get the same value. And what's 2 times 2? 4. Ah. Okay, so what if I did this then? What if I went to 6 times the charge on one of them, on Q2, but the first one remained the same? This is the value, right? 134.813. 134.813. Okay, so then how about this? What if I doubled one of them and tripled the other? Sure. 134.813. And what's 2 times 3? And then 1 times 6 is... So when you multiply our charges together, that is going to be how they're directly related to our force. So in our lab, what we're going to do is we want to see how the electrostatic force, all right, is related to the size or the magnitude of the 2 charges, Q1 and Q2. Keeping the same distance in all the trials, systematically alter the charges of the objects and record the force. Be systematic and use purposeful changes. Don't just go random. You want to see what as you change, how it changes. Okay, we got to think scientifically here, and I give examples such as doubling, tripling, quadrupling. How is that going to change? So let's pick a starting point. Okay, I move this one all the way to 0 centimeters, and I move this one to 2 centimeters. And I'm going to say, all right, I'm going to pick this. 1 and 1. Now, the unit here is microcoulomb. The unit for charge is the microcoulomb. Or not necessarily microcoulomb, but it's the coulomb. 1 coulomb of charge is relatively large, so we generally see them as micro. And micro means 1 millionth. So how do I get that symbol? So I'm going to type in 1. I have to go to insert special characters, and I can type the word micro up here. As I do that, I get the micro sign. It's the Greek symbol mu. So you type in the word micro, and then you go to this little, it looks like a U, lowercase u with like a booger hanging off the front.
Wait, so how did you do that again? I'm sorry.
All right, so that's fine. You're going to go to insert.
All right.
You go down to special characters, and you can type in here where it says search by keyword, just type in micro, M-I-C-R-O, and it should be the one all the way to the left.
All right.
Now, microcoulomb. Coulomb is capital C. Q is the symbol for charge. Q is our variable, right? So like for force, it's capital F. For acceleration, it's lowercase a. For charge, it's Q. All right, you can see it can be either though. It can be capital or lowercase. It depends on, all right, whatever source you're looking at, book, website. Now, what I'm going to suggest to you guys is to highlight the microcoulomb.
Why? Because we're going to copy.
Yeah, you're gonna use that for a bunch of stuff. So I would do that and Control C to copy that. Okay, the first charge we said was over here was 1 microcoulomb. And what was our force? 22.469. Force is always measured in newtons. Doesn't matter whether it was gravitational force, Newton's second law, electrostatic force. Yeah, this is what we're good. So this, guys, is our baseline. When we have 2 charges, both chilling at 1 microcoulomb at a distance of 2 centimeters, this is what the force exerted on each charge is by each other. So when in the lab, it says here, guys, to be purposeful with your changes, right? Such as doubling, tripling, quadrupling. Here's why. So we can try to come up with, all right, a conclusion based on our data, right? Why do we like try things? To learn, right? Like when you throw a baseball, if you throw a baseball at a low angle, it doesn't go very far, right? As it does maybe if you throw it with like a different angle. So even though that's just basically trial and error, it's trial and error, but you have like a purpose to it, right? You've tried it, like, okay, well, if I throw it at this angle, but if I throw it harder, you may go farther, etc. So next, I'm just going to change one of the charges. I'm going to change just one of the charges. I'm going to double Q2. I made that 2 microcoulombs. And now I'm going to write down these forces, all right? So I have 44.938. So that's what we're going to write here. 44.938 newtons. We still had 1 microcoulomb here, but we changed this one to 2 microcoulombs. And so what is good, or what is going on with this? Well, I doubled one of the charges and the force doubled. That's good. What if I tripled just one of them? So I'm going to make the second one 3. And how do you think that was going to affect it? Anyone have an idea? Do you think it's going to triple, right? Because all we did right now, first one, we doubled one of them. Now we should, the force doubled. So if by tripling one of the charges, that original value should triple, not this number. Okay, because we're doing everything based off of this value, the original baseline. So if we triple that, we are going to write down 67.407. And very good. Okay, so it tripled. All right, one more. Let's do another one. Let's quadruple it. So by quadrupling it, one of them would be 4 times the original value. So we have 4 microcoulombs. So if I go back into the simulation and I increase this to 4, now I have 89.876. 89.876 microcoulombs. Okay. Okay. Now, so that's interesting. We have this idea, right? Okay, well, what happens, guys, if I decided to double both charges? If I double both charges, what? It's now going to be 89.876. Okay, so let me see. I made this one 2 and this one 2, and now I have 89.876 newtons. So, okay, I doubled one of them, the force doubled. I tripled one of them, the force tripled. I quadrupled one of them, the force also did the same. When I doubled both of them, it increased by a factor of 4. Are we adding then? Because if I were adding, right, 1 plus 4, this should be 5 times. 2 plus 2 would only be 4 times. So what? So then let's just try this for a second. 1 and 6, what do I have? What value? 134.813. Okay, so this would be by increasing one of the values by 6. So if this is increased by a factor of 6, over here we increased the 1 by a factor of 4, and then we just doubled one of these. Notice they had the same value. What is 2 times 2, by the way? Anyone? So I increased this dude here from 1 to 4. So what's 1 times 4 is 4. This value here, this 89, is 4 times that. And over here, I doubled both of the original. 2 times 2 is how much? 4. And so I get the same value. So that should lead me to believe that if I do 1 times 6, I get this value, which is 6 times our original.
So
What's
2?
Let's do 3 times 2. So let's double one of them and triple the other.
Oh.
Aha! Now we see. So I could say, let's make this one 2. Let's make this one 3. And this one should be what? 134.813. 813. Now I'm just going to add one other column. I'm going to right click here, and I'm going to say insert row below, and I'm just going to write this 1, 6, and it's going to be the same value, this 134.113. I'm doing that so you guys can see that, okay, this is our stat baseline. Doubling one doubles the force. Tripling one of them triples the force. Quadrupling one of them quadruples the force. But it's not just limited to by changing one of them, because if I doubled one and I double the other, I also get the same value. 2 times 2 is 4. 1 times 4 is 4. So it seems to be the fact that the force is directly related to the charges, but not just the charges or adding them, it's by multiplying them. Do you think that makes sense?
Yeah.
So how do I know it's a direct relationship? If I increase one, the other thing increases. That is basically essentially a direct relationship. So if you were to show that in an equation form, okay, so make a claim the force is directly proportional to the force is directly proportional to our charges. And if you had to write that in an equation, Well, F is going to equal, we have Q1 and 2. Or were we adding them, or were we, what do you think?
Wait.
Well, 1 plus 1 wouldn't really work, right? 1 plus 2, multiply, good. So Q1, how do you do the subscript? Control what? Control comma, good. Q sub 1, and then Q.
How do you go back?
Control comma again will set you back to the original. Q1 and Q2. And again, like what we have said, right? If we said, hey, let's change everyone to a 1. But right? So these guys both represent both of the charges. So if I double only one of them, doesn't matter which, what happens to the force? Yeah, it would double. It would be 2 times the original force, which we saw up here. Okay, like what if we quadrupled one of them, just one? What happened to the force? It would be 4 times. And you could show this mathematically by taking this value divided by this guy, and it should come out to be, should come out to be 4 or very, very, very close to. But what if I said, okay, well, let's double both charges. So instead of them both being originally a 1, what happens? What's 2 times 2?
4.
4 times the force. So this is showing, guys, referencing our data, showing how, all right, our data supports our claim that they are directly proportional to the charges. Could we say something even further? Could we make this a little bit better? Not just proportional to the charges, but proportional to the
Force.
What is the word, right? So if you add things, it's the sum. If you subtract things, it's the difference. What is it called, like when you multiply two things?
Yeah, the product.
The product. So the force is directly proportional to the product of the charges. That would make it better, right? I agree. That would make 100% more sense, and that goes very good with our data, and especially the simplified version that we just showed right there. That. Now, no. Don't do that. Okay. Oh. I don't know why that jumped all the way down here, but it did. Now, challenge number 2. How does the electrostatic force relate to the separation distance between the two charges? So keeping the magnitude of the charge on both objects constant. So we're not changing the charges. We want to do a systematic study to collect data relating the separation distance to force. The separation distance is defined as the distance between the centers of the two objects. The best strategy involves centering the objects on a grid line using distances that are whole numbers of squares. Okay, so I'm going to scoot one of Q1 all the way down to 0, right? And we have to line up with the centers. So I cannot get the center of Q2 to be on 1 centimeter. But I can get it to be straight above number 2. All right, now let's go back to chilling here with these dogs. Woof, woof. Skirt. Okay, so this is going to be our base value again. These two charges are separated by a distance of 2 centimeters. Okay, so we're going to say, what do we got up here? Separation distance is 2 centimeters. And what is my force? Now, again, we're keeping the charges at 1 microcoulomb. Technically, you could do this, whatever. If you wanted to make them both 4, whatever, you could do that as well. But I decided to make mine 1. Okay, now what is the force between them? 22.469 newtons. So that's our base. Okay, so guys, let's double. Let's double our distance between them. All right, so what's double of 2? So let's go to 4. Okay, now did the force increase or decrease? It decreased. Now what is the value here? 5.617. 5.617. 5.617. And this dude here was 4 centimeters. Okay. So the next one, what would be, if we go back to our original, what is 3 times?
6.
So let's go to 6. So when we triple our original distance, dang, it decreased again. So now we have 2.497. So as I'm seeing, as the pattern kind of is emerging, as I increase the distance between the two charges, the force decreases. So then obviously if we said, okay, let's change this to 8 centimeters, do you think it's going to be more or less than this 2.497?
It looks like it's decreasing, so less.
It's going to be less. Okay. So again, now what was the original value? It was 2. Double of 2 is 4. Triple of 2 is 6. So quadruple of the original distance, 8. What happens? What is our force? 1.404. Okay. Now, what I wanted to show, or what's going on here, is noticing this. By doubling the distance, the force decreased by a factor of 4. When I tripled the original distance, the force decreased by a factor of 9. Mr. Lombardo, wait, how are we getting these numbers? So what I did was I took, let's say this. All right, I did 22.496, and I divided that by 22.496. You guys don't need to worry about that. You guys aren't doing that. I'm just doing that there to show. So 22.496 divided by this 5.67. And I get a value of 4.0048. Yeah, decreases by a factor of 4. Okay, now what if I divide by this 2.497? It decreases by 9.00921. When I divide it out by the number 1.404, I get 16.022. Now, what do you notice, guys? What do we notice then? By doubling the 1, this decreases by 4. By tripling this thing decreases by 9. And by increasing the distance by 4, the force now is decreased by 16. What do those numbers have in common? Or what is there a pattern there? I want to see if you guys can come up with this.
5.
No. It's okay. So how are 2 and 4 related?
They're multiples.
They're multiples of each other. Okay, right? Okay, well, how is 3 and 9 related?
Because times 3 is 3 and it's 9.
Okay, and how is 4 and 16?
4 times 4 equals 16.
So they are the squares of each other.
Okay, that makes sense.
They are the squares of each other. So by that pattern that we just developed, if we made this one here 5 times the original value, all right, because 2 times 5 would be 10, that means that this one should be decreased by a factor of how much?
Wait.
So 10 squared?
No. Right? So this was the original distance. The original distance was 2, and this is our original value. When we doubled our original value, this decreased by a factor of 4. It decreased by the square. Okay, when we tripled the value from 2 to 6, it decreased by 9 times. When we went to 4 times as much as the original, it decreased by 16.
So 5 would be 25?
So 5 should mean it should decrease by 25. So I'm going to do this in my calculator before we even go there. I'm going to do this 22.496, and I'm going to divide that by 25. And my calculator says it should come out to be 0.8998. That's what it says it should be. Now let's see if it's right. So here was it originally, and now it's 0.899. It's pretty good, I think. Yeah. All right, so you can even get rid of that 8 if you wanted or needed. So what pattern has come across?
Multiples.
Squared.
It has to do with what? How is the force? How is force and distance?
So every 2.
Well, first let's ask by this. Are they directly proportional or inverse? As one goes up, one goes down, so it's inverse. Okay, so force is inversely proportional to what? The distance. So now, what that would mean, if I just said that, okay, well, that would say if I double the distance, force should be cut in half. If I triple the distance, the force should be cut into a third. What was that happening? No, that wasn't happening. What was happening? What was happening? Decreasing by what?
9.
4, 9, 16. We said 25.
Doubles.
Not by doubles, but
Multiples. Squared.
the squares. All right, so force is inversely proportional to the distance squared. And now if you had to put that into an equation, F equals whatever's on top. We don't know what's on top. Divided by D. How do you write the square? Control period to get the superscripts. Hit the 2 button, boom, control period again to put it back down. So that is how force is directly, or how is the force is proportional or related to the distance. Now, if you guys vaguely remember, when we briefly talked about universal gravitation, the equation's up top over there. F is equal to big G m1 m2 over d squared. It's an inverse square law. So what has a greater effect on the force? The distance or the charge? No, the distance. Because right, if you doubled just one of the charges, but you double the distance is cutting it into 4, whereas the other one's only increasing it by 2. So like those are direct. This one is inversely proportional to the square. So if I increase one of the charges by 4, force increases by 4. But if I increase the distance by 4, it's dividing it out by 16. So the square has a huge play on it. And we kind of saw this in the beginning. So let's say this is the original value, the original distance. So let's just say, hey guys, this is our original piece. If I brought two charges closer together, so if I cut that in half, right? If I cut that in half, that would make it to 5. All right, so let's look at our original value, this 8.99. If I cut it in half, what do I get? I get this 3.95. So how is that related? So 0.899 And if I multiply that by 4, that comes out to be this value. 0.899 times that by 4 comes out to be 3.596 or 3.595. So it works that way as well. If you shrink the distance, all right, you cut the distance original, like in half, all right, so you, instead of them being out here, you bring it to half of the original distance. Well, now it's 1/2 squared on the bottom, 1/2 squared, which would be 0.25. You flip it, be the same thing as multiplying it by 4. If you did it to 1/3, that would be timesing it by 9, the force by 9. If you bring it to 1/4 of the original distance, by 16. If you bring it to 1/5 of the original distance, 25. Okay. I don't know if we can even get to that. Let's see. Well, what's 1/3 of 10? It'd be like 3.33-ish. So 0.899 times 9. This would be 1, 2. So no, this should be. Can't get it quite here. It should be like in between these two. Can't get it to be exact. Or 1/4. That'll be 2.5, which should be somewhere right around there. So that'd be 0.899 times 16, which would be like 4.384, which is almost the exact, yeah. So that, guys, is going to be how our charges and our distance directly relate or affect the electrostatic force. And again, right now, how do I know what kind of value I have? How do I know what the charge is, whether it's attractive or repulsive? Well, not necessarily that. Well, yes, the color does change. But looking at the vector, are they angled towards each other or away? Okay, now one of them is negative and one's positive. Now are they towards each other?
Yes.
Okay, what if they're both negative?
Away.
They're both away. Okay. So with all of that being said, suggest an equation that relates the force, the charges, and the distance in the form of, all right, the force is equal to K, and K is the proportionality constant for Coulomb's law. We don't need to worry about that value. So this is how our equation should start off. K. Now, basically, just combine your two equations from point 1 or part 1 and part 2. Challenge 1 and challenge 2. What was our equation in challenge 1? Did we not make one?
F equals Q1 Q2.
Q1 times Q2. And over here, we said F is equal to 1 over D squared. So combining those things, so you would have Q sub 1 times Q sub 2 divided, right? If I said 1 on top times 1, anything times 1 is itself, so do I even need to bother with that? Right, from this equation? No, I don't. So what should be on the bottom? D squared. Now, this doesn't look as nice as I want it to, so I'm just going to actually insert an equation. You guys don't need to do it like this, but I am going to.
How do you do the K thing? Insert and then formula?
Whoa.
You guys don't need to write this equation. I'm doing this because I just think it is better for y'all to see it like this. So this, basically however you write it like that, I mean, this is what it would look like. K is a value that will be given to you guys. The charges are whatever you're given, multiply them together, and then divide it by the distance that separates their centers squared. Okay, so you guys, when we have that all completed, okay, you may submit that. Yes.